Okay, so can everybody see the slides? I just need to see. Yeah, Mike says yes. Okay, awesome. So as I was talking before, is basically it's taking something so we don't have to obviously use a lot of humans, but they're derived from humans. And the key first step is this stem cell stage, pluripotent cells. And then you're growing these over the course of months to form this organoid. And then over the course of time, drug screening, and that's to benefit the patients before. Now, what I'm going to be talking about tonight is basically there's opportunities in quantum technologies, including sensors, computing, and algorithms to improve the instrumentation that's used along with this development. So in specific with sensing, you have opportunities for better sensitivity, better resolution, and also to increase our understanding as well with computing. So in computing, you have simulation, quantum accelerators, instead of just a GPU, CPU, now we're talking, a QPU that could do tasks that the other two aren't quite as good at. So as an introduction here is that after reading this paper, and I've, just reading a lot of these papers as far as what neuroscience needs, is that the future of brain organoids needs improved instrumentation. Now, this instrumentation isn't going to come from a lot of today's technology, and it's going to need these quantum technology, in specific, the three I mentioned, which are sensors, computing, and algorithms. Now, the thing is it's an emerging field with quantum. However, in August 2022, so basically a day ago, last month, that there's these new sensing technologies, like I mentioned before, is you take a diamond, and then it's an impure diamond. No diamond's 100%. You'll have it's called a nitrogen vacancy. So nitrogen has 3 bonds in the diamond, leaving an open hole instead of a carbon there. And then to do these types of sensing applications, getting better resolution, in millimeter resolution in cardiac applications as well. Now, the big news that everybody's waiting for is an NSF believes that next year we'll have a practical quantum computer. They were the first to fund quantum computing. And then, so it's one of those things where it's, since the early 80s, the quantum technologies are a government initiative. And I think that gets lost a little bit in investment. Is basically, they've been behind all of this, from the beginning. They've seen it since the early development of the first quantum computers. In sensing, the term is a little bit looser. So MRIs and lasers are technically quantum sensors. And then these types of things will develop over the course of time. Here, and then as you see, so anytime you grow something in a lab, it's going to be different every single time you do it. And the goal with a lot of this is for when you're growing organoids is basically for them to be reproducible. When you're doing experiments in the lab, you don't want deviation. And that's what they say in the future, these things will get a lot more reproducible and, creating these 1,000 cells. So as the technology evolves with live cell imaging, you want to be able to see what you're doing, and just researching a lot of this stuff as far as the different microscopy techniques for visualization. You have statistical analysis for computing as well, is that you really want to, use the emerging technologies that are available in quantum and not to delay with it. So that in everything with the human brain is you want to see up close what's happening. So it's kind of like taking like a camera and you're zooming in and out. So say if we're at this certain point right now, we really want to be able to zoom in a lot more closely with this. And a quote in this article, it says, brain organoids composed of roughly 1 million cells have neuronal assemblies of sufficient size, cellular orientation, connectivity, and co-activation. So it's basically saying they're appropriate to do neuroscience research. And the future of this is basically accelerating our understanding of signaling. I mentioned before, studied signaling before, is it's a very important thing because we want to see ultimately how things are with humans in cognition, like how we think, those types of things. So we've had minor little advancements with that. And also with that, we want to understand cell fate, neuronal migration, and neurite extension, and uncovering additional interactions of the human nervous system. So we're not just the brain, we have other nerves in different parts of our limbs. And that's basically one of the things that we want to understand is how does it all connect with, you have like motor, sensor, neurons, these types of things, and especially with the brain. Now, the future of this with medical instrumentation is basically, so this again, a lot of this is coming from this, the next 50 years of neuroscience. So they believe that advances in microscopy, and again, this isn't just things that are micrometer in length, is nano and beyond as well, is that it will become broadly accessible. So a lot of these statements that they had, I think were based on the previous 50 years and how far we've advanced. And then especially seeing it, how fast things are going to advance in the next 50 years. And to look at subcellular machinery. So basically, if you have like subatomic particles to an element, to a molecule, and then you have these molecules that make up the subcellular machinery with unprecedented resolution. So it's going to take significant technologies in order to do these things. And one of the things that we're seeing in sensing and computing is that quantum technologies looks like it has a very good future in solving a lot of these problems. And especially like when you have anything, if you see a lot of these pictures, fluorescence and dyes and these certain things, there's only a certain amount of zoom that we can have. They say due to the Heisenberg uncertainty principle that it's impossible to see both position and momentum at that same time. But getting closer and closer to that kind of single atom resolution that we're looking for. Now, this quote is interesting. It says, improvements in biotechnological methods and imaging instrumentation may help in establishing astrocyte neuronal interactions. So that's the thing is like this, the brain was once quoted, I think quite recently, as the most complex device in the universe. So we've heard of things as, neural networks, basically taking this architecture that we have in the brain. And even more recently, we have, it's called neuromorphic computing. So it's conventional computing as far as I know, but it's doing both processing and memory in the same location, i.e. that's how our brains act. So although we might have a supercomputer, quantum computer that's faster than our brain, as far as what's accessible to us today, it still appears that the brain is best at it because it does both processing and memory in the same location. So it's basically getting new understanding of circuit functionalities. And then you see, when you're talking about machine learning, obviously you're talking about computation. And in this article, this next 50 years of neuroscience, it says statistical and computational methods will become essential. So it's very important that, once we sense whatever we're gathering, that we want to be able to see it in an effective way, do visualization, do statistical analysis, these types of things. And they say that organoid analysis tools, so single cell profiling, cutting edge imaging, and functional interrogation methods need to be enhanced. So these types of things, if you're talking about, if we have billions of neurons in the human body to basically to understand, closer, that it will take significant computing algorithms and also the sensing developments that we've been experiencing as well. So this page I really want to highlight. So if you ever research on nature, you'll find that it's pretty hard to get into. We do generate a lot more articles than we used to, but still the quality is still very high. And these two specific articles I was very impressed with. So as I mentioned before, so for those of you just coming, a nitrogen vacancy diamond quantum sensor is something that takes diamond, so like little small pieces of diamond, and it has nitrogen defects in it. And since nitrogen has 3 bonds, it has a vacancy right next to it. So that nitrogen vacancy interaction allows for us to do this quantum sensing improvements. So in specific, heart magnetic field detection from centimeter to millimeter resolution. This was done open heart on a rat, and they listed a bunch of things. So if it's basically, for those who have a technical background, it's like if you have a signal to noise ratio, we want more signal on the numerator and less noise in the denominator. And so this has high hopes for that, basically. So if these two hold up, this type of sensor could have a very big impact on sensing. I just researched, it's like a quantum chemical sensor that uses the chemical as the qubit. So it's called a triplet excited qubit as the chemical. So these in specific, these two, use a solid diamond with that NV vacancy. Now, the one that's really interesting as well is they took the Martin Luther King "I Have a Dream," like a 3 or 5 second clip, and they made it a lot clearer. So with anything, when you do see something kind of unique or worth looking at with all this stuff, is that you'll have to see how this holds up versus today's classical conventional kind of ways of decreasing noise in these systems. But again, a lot of these things, this diamond sensor that these two use, I think the development started as early as 2015. So they're not something new. It's just one of those things. There's always going to be more computing news, but in specific, these kind of stood out as far as last month. Now, how is all of this going to get done? Is basically these things have been emerging since, so we had Google Quantum Supremacy in October 2019, and then AWS Braket announced in December 2019 that they'd have a quantum cloud service. So initially it was very limited. So only very few people had access to the service. The following year in 2020, Amazon allowed for more people to use it. Now, last year in November, they announced hybrid jobs, which allows you to send a specific task up to the cloud and then to analyze it both conventionally and classically, doing most of it conventionally and the things you can't with quantum. And this is important because also NVIDIA, so I talked about this before, so some of the goals with quantum computing is basically better statistical analysis, visualization, optimization, and to use these quantum accelerators, more lower qubit count, lower, basically smaller quantum computers, and for simulation too, when you're trying to simulate something. So there's also quantum simulation on the hardware that you're running on classical hardware, but in specific, simulating things in the outside world with these hybrids. So NVIDIA Coda basically has a CPU, GPU, QPU on the horizon. So that's definitely worth checking out as well. Now, as far as quantum algorithms, they're the secret sauce to running on these things. So once even with sensors, computers, they need to be told what to do. So Quantum Algorithm Zoo has hundreds, probably hundreds, and they've been compiled over this past 10 years. And also Classic on June 2nd of this year announced that they have innovative ideas into competitive advantages, i.e. you can use quantum algorithms on AWS's Braket. So as I mentioned before, so here's the summary. So the future of brain organoids needs improved instrumentation, and that instrumentation needs quantum technologies. In specific, what's emerging right now is in sensing, and then moving forward, there's, as early as 2023, we're going to start to see applications that are a little bit more advanced than what we're seeing here. So it's very interesting that, let's see here. Okay, it's very interesting to see the development, not only in computing, but especially in sensing. And if you go to its quantum.gov, they have on their second one that you can click on, is coming. It's called quantum sensors coming to fruition. So many of the things we'll see even in computing is different aspects of sensing, lots of different hybrids. And again, in the science world, and especially neuroscience and kind of like this brain organoid thing, you'll start to likely see this incorporate into the medical instrumentation that needs, better resolution, less noise, addresses limits of detection, and especially sensitivity as well. So these things will continue to build and grow. Like I said, it's a government initiative. So we have that. If they put it at $1 billion in 2020, in 2020, 2020, in 2021, we saw $3 billion in private investment. So it's a very interesting field. I wanted to introduce a bunch of people here. So again, it's good to see kind of like first people on. So Mike, like I said, Karma, good to have you on. Nardo's been on before, and I want to introduce Austin. So Austin's been on the panel before, and he's a tech in this area, and so he works for the VA, and he's very experienced. Now, as far as all of this, Austin, what kind of stuck out to you as far as maybe today's slow processes, something that couldn't exist today without something with emerging either sensing or hardware? Did anything stick out to you, Austin?
Definitely what really stuck out to me with this was the idea of observing the relationship between, for example, the astrocyte and the neurons in real time, as opposed to just in vitro or outside the body. So that was really stuck out as something very promising and interesting. It'll take a lot of the guesswork out of like what's really happening, and are we really modeling these processes correctly?
Yeah, so we're talking about simulation too here. So an important thing that we could talk about neuroscience for forever is basically there's different techniques. There's called invasive. So this is like the Elon Musk project, where it's literally drilling into your head and trying to access neuron by neuron information, i.e. the best. Now, the ones that might be the most mainstream are called EEG, MEG, MRI. So they use either electrical or magnetic information from the brain. And then more commonly, it's magnetic. So does anything, as far as that kind of stuff, like the magnetic information, now that diamond sensor that was announced twice, two different kind of publications in Nature, that uses magnetic information from the heart to achieve that kind of millimeter resolution that we're looking for. Does anything kind of stick out as far as that, Austin, as far as like, okay, we'll be fine doing things non-invasively, or do you think there's some compelling reason to basically trying to get neuron to neuron, studying a single neuron at a time, invasively?
Oh, that would be very interesting to try at the very least, to see if you could narrow it down. We see this sort of already with when they do an EEG surgically. So they'll remove a part of the skull and they'll actually place EEG electrodes on the brain, and they will try to pinpoint the specific spot of the seizure, and then once it's isolated, remove it surgically, just all at the same time, all in one go. So in that sense, that would be fantastic to see that from a surgical sense, because it would be less brain tissue that they're taking out. The more pinpointed down we get, the better. The better the surgical rates will be, the happier the surgeons will be. As for what you jumped out there in terms of surface level, that would be useful for probably finding damage outside the brain. So there are a lot more, while the brain has a lot of neurons, we've had a difficult time, EMGs, electromyographies, pinpointing specific nerve damage from nerve to muscle. in that case, or neuropathy, nerve damage, and then ablating, or ablating meaning burning away certain nerves. We kind of just right now we do large nerves, so big nerves. There's something called a small fiber analysis, where you take a needle, you insert it into different singular nerves, and you're hoping to pinpoint which singular nerve is causing the neuropathy, the pain. But we haven't, that's rare. I see that rarely done, because it's the specificity is usually called into question because of how many there are. So that would be interesting in that, as an application in that environment as well.
Very interesting. I mean, the way that you talk about it, it sounds like invasive surgery is common. Do most hospitals do this?
On the EEG side, not usually, because most of the most seizures usually are not singularly focused like that. So usually you'll see that with like temporal seizures.
Okay.
You'll see them perform that surgery a lot with that, because it's easy to isolate. And how the disease works is that it is singularly focused in one area of the brain, so you can't take it out, and know that you will be seizure free. You hopefully be seizure free from that point on. But as for the small fiber neuropathies, that's more just to go in and stop like the pain from nerve damage from anything from hurting your toe to diabetes. So some outside disease. So
yeah, very interesting. I just feel that hands-on experience there, which is very interesting. I'll get you, Nardo. So one of my colleagues, he helped design the first. It's the pulse oximeter by Nellcor, and they said that the two main things were non-invasive and predictive. So the LEDs that they used were bad, or they couldn't predict the quality, and the algorithm would account for that. And I'd say the other kind of thing is wireless. So those three things are kind of like the holy grail. Obviously, operating on battery, those types of things, because with the twisting and turning of patients, if they're awake, those types of things has is an impact. So Nardo, I saw your comments. So you said, can quantum sensors be used in a therapeutic capacity?
Yeah, I'm trying to figure out whether it's the quantum sensor itself, or quantum capabilities, or quantum properties that could be used in a therapeutic capacity.
It looks like, so this is on a rodent, so this is on a rat, and then I can post that article. So this is the Nature article. So this month, or actually in August, Japan was just quantum sensors, quantum computing, all this type of stuff. So basically with the results, Nardo, is they're saying that they got millimeter instead of centimeter resolution. And it seemed like, as far as I read it a couple times, like the problems with it are coherence, like with the rest of quantum industry, and then something with like a inline amplification. But beyond that, I couldn't find too many other things as far as issues with it.
Yeah, because a lot of these sensors are pretty much more for data gathering and monitoring and stuff like that. But quantum has really weird properties, right? So from a physics and mechanics perspective, and there's some level of potential manipulation you could do from an atomic small particles standpoint. So I was trying to figure out if you could do a non-invasive approach in the brain therapeutic side using just the quantum properties.
And you're saying to make the subject better instead of just sensing.
Right.
I haven't come across, and most of these, I think at this stage, even if NV diamond sensors have been around since 2015, if not before, I would read it's the quantum.gov, and I think it's typically, but it says, quantum sensors coming to fruition on their website there. I think it's typically for detection. I haven't heard anything, because it's like how Austin was talking about, have you have electroencephalography, magnetoencephalography.
Yep.
Well, this is just so the emerging one right now, or has been working, it's called OPM MEG, which is like the skull cap and it picks up magnetic information. They make comparisons to that as far as, better, aspects of this type of quantum sensors than the one that's kind of moving up now. But I think typically with sensing it's for detection.
Yeah, no, I understand that it's primarily for detection, but I think quantum has such weird capabilities and properties that I think with quantum we haven't imagined a lot of these different things as well, right? So it'll be interesting if somebody would come up with thoughts around that.
Yeah, it's definitely interesting. Now you're talking about, so quantum computers run off linear algebra, complex numbers, and quantum mechanics. Now the qualifications to be called a quantum computer are somewhat more strict, like you have qubits, entanglement, superpositioning. Now with quantum sensors, just anywhere along that process, like lasers and MRIs are technically quantum sensors, it's acting on some form of quantum mechanics.
Yeah.
So that's typically the definition. So even the OPM MEG is called a quantum sensor, and that's the one where instead of sitting in a thing kind of like an MRI, not quite as big, now you can wear a skull cap, and it uses the quantum mechanics property of atoms adjusting to the femtotesla magnetic information coming from the brain.
Yeah, there is one such startup in Colorado that basically does this already, that I know of. And they have a level of sensitivity that is unseen before. So excited.
Okay, and are you saying detection, or are you saying for output?
Detection.
Okay.
Yeah, they're basically at like 1,000 times sensitivity and fidelity.
Yeah. So, and again, so for everybody else, is like, with quantum sensors in specific, it's a loose term. We're typically not talking about, entanglement, superpositioning, these types of things. But with this Nature article, they got tenfold, right? So if you try to imagine, you have noise, right, and you have signal, it's basically accounting for 10 times greater signal or 10 times less noise, however you look at that. And due to that, there's a bunch of things in neuroscience. I think maybe they listed like 4 or 5 things kind of lined up if we only had better detection, and then i.e., quantum coming in. So yeah, it's very exciting. So yeah, it's good to hear the Colorado startup too. Anybody else we haven't heard from? Feel free to unmute yourself, or you can come on. There's other people kind of in, I'd say, medical too. So it's good to see Ron. So Ron's been on pretty much every episode, maybe the last 3 or 4 months. And here comes, I think, John. Okay, go ahead, John.
Hey, guy. No, I just like the detection, because anything that's non-invasive basically throws bias into the situation. So even though the brain doesn't supposedly feel pain, the brain does notice things, from what I know about it. And I did some stuff with a medical company. So we did lasers and tissue ablation, a bunch of little physical things for just general surgery. So I'm quite interested and still interested in what you can do with all this technology. I was at a brain conference in 2018, listening to some people discuss about the amount of Chinese people that have epilepsy. And I was thinking to myself that, if we could detect harmonics, you could detect the calm before the storm. Because to me, anytime you have a storm like at the tail end of epilepsy, you've got a series of harmonics that start out as an oscillation, and then oscillation starts to build. Just to cut the tissue out, that's disgusting. That's what they do. And the key would be to be able to detect that. That way you can find ways to basically quell the harmonics before they get to the point of rattling the person's brain, at least that neural set, and disrupting all and it comes, apparently, the more I study epilepsy, the more I understand how epilepsy affects a lot of different people, a lot of different ways, either at that one massive storm or basically on a general basis. So it does affect behavior. And once you start noticing that, you'll start to notice people start to do a little tremor. So, and it's kind of funny that I throw that in a political sense for certain people in parties and stuff like that when I start to listen to what they don't have to say. But, if you can look at the storms and find the base harmonic and figure out why that harmonic is being generated. It's base. Cutting it out is the last stage of something you don't know because you can't treat it. And so what these guys are doing, what you're talking about in Colorado, pretty much is a step forward and doing that non-invasive, kind of figure out where the signal is getting interfered with and why there's something happening in the link that basically causes that to oscillate to the point that that is totally disrupted and that person goes into shutdown.
Yeah, this is definitely good to hear, especially with all the background you have with this. And not only epilepsy, Alzheimer's, dementia. Now, to further simplify this to everybody, is basically when you're doing sensing, detection, these types of things, and you have a cleaner, more signal, less noise, is it opens up the opportunity for better prediction. And John was hinting on, John said that too. So these types of things are definitely worth, like even I might read the heart one in specific 3 times. Is you really want to see what the issues are, and then how quickly can they be resolved. But like I said, when I read it a couple of times, I didn't see too much wrong with it. And it had a lot of as far as like researching in academia for a while, it had a lot of the aspects of, basically providing as much detail as they could. You can ask them for additional supplement. In the sound waves, so in sound waves, we could be talking about ultrasound, for instance. They took the Martin Luther King and, I Have a Dream, and basically removed a lot of the noise. Now, the thing that'll hold up is basically how does that compare to AI? In today's, keep in mind, we still have awesome, conventional computers, these types of things, but it's worth heavily researching these things as far as, prediction, or as far as like predicting when they will come for human use. But they're not new, I wouldn't say, as far as the diamond sensors that have been out for a while. But these are the kind of 2 that stood out. Now, anybody else that we haven't heard from? So Ron actually is in that, or actually, go ahead, Mike. Yeah, you're on mute, Mike.
So I would encourage you to continue to differentiate between your quantum sensory and your quantum computing.
Okay.
Because quantum computing exists to solve a subset of problems that regular simulation is not able to solve. And what you see in AI and everything else is high computational rates in linear algebra to solve problems. And what quantum computing offers is the ability to take advantage of the quantum world to solve combinatorial problems where you have to search all possible combinations. And that's all very interesting, but I don't think you should be distracted with it, because I like what I've been hearing you doing, which is trying to comprehend through quantum sensoring what is going on in the human brain. And do not get too far down the path of expectations of quantum computing, which is just solving combinatorial problems, which exceed the grasp of regular simulation computing.
Thank you. And I would agree with that. So I think they're doing these hybrid things, CPU, GPU, QPU, because there's certain aspects that quantum off the bat, say in 2023, will have advantage for, and still the bulk of the work will still be done CPU, GPU. And as it progresses, you'll see more of the load being put on QPU, quantum processing units, as well. And I would agree, as far as right now, sensors are definitely kind of coming to fruition, as the quantum.gov article says. And then, so we haven't heard from a couple people here, so still waiting for Ron. So Ron does kind of, go ahead, Ron.
Yeah, I haven't gotten to read the paper you shared with me yet, Kevin. But I'm definitely, it's definitely on my list, and it's going to be interesting to really dive into this whole diamond sensor with the nitrogen vacancies. I've heard some things go around about it, about how it's created, and I'm hearing some conflict in the understanding. So That probably just means it's real new. I mean, it's new to some people. You said it's been around. But one thing I'd like to see is, obviously, to get high resolution, you need more than one sensor, right? So are they building these quantum sensors in arrays? Is it how they're getting? I mean, obviously, the precision has to do with what one sensor, what the sensitivity of one sensor is. But do they use it like an array, like in a camera, like in a photo array, so they can actually, like focus it down onto a specific area, like in the brain or something like that, and create a 2D or a 3D image? Or is it just one sensor where they're trying to analyze the magnetic field around a specific point? So those are things that I hope to learn by going through that paper. But other than that, it just seems very intense that that this sort of technology can reduce the noise and bring out more signal, like you were saying, like the Martin Luther King tapes. And I threw a comment in there. I said they need to go back to the Nixon tapes and find the
18 minutes.
use the quantum technology to recreate the signal that isn't there anymore. It's just all fascinating technology.
Yeah, I would say as far as it depends on the application, as far as the number of sensors, is if you want additional information all across the head, non-invasively, wirelessly, all these types of things, then that's for that. Now, the one that they did on the rat's heart, it was my interpretation that it was just one, but I could be wrong. So I'll probably wind up rereading that one. And the other things that you talked about, and even kind of going back to what Nardo said, 1,000 times better for this, startup in Colorado, very encouraging to see, basically pinpointing the type of quantum technology that's actually really moving a lot faster than the other ones. So also for those who are interested, so Nardo has a pitch competition. You could read about it in the details. It's good to see that, Nardo. That means that the technology is definitely going somewhere. It reminds me of the Duality Accelerator, how they offer like 50K up front if you're basically incubated with them. Now, anything else? Okay, so the other stuff that Nardo put in the chat here: gravity, temperature, pressure, rotation, acceleration, frequency, and magnetic. Yeah. Now, the kind of other ones that are very interesting, I researched this in Japan in August. Sensing computing, like the quality of this article, it's like an ARC exchange. It's Chem XRIV, so it's basically not peer reviewed yet. They took a chemical and used it as a qubit, and they excited that in a metal organic framework, introduced different analytes to it, and the ones with aromatic rings, i.e. like DNA and certain amino acids off protein, they're the ones that had the highest sensitivity. And actually one of them they put in, which is 5-fluorouracil, which is the anti-cancer drug it's called 5-FU. Anti-cancer drug for breast cancer, that had really good results too. So that one's worth checking out as well. I didn't put it in this pitch deck, but if you're interested, I could send it to you. Now the other ones we talked about as far as kind of position, there's an attitude quantum sensor that's been in the news these past couple weeks, and I would check that one out. And obviously we've talked about magnetic, electric. The big kind of thing is magnetic information from patients. So go ahead, Ron.
Yeah, you had I believe you had a speaker in your group a couple months back who was also talking about the nanowires sensors, and I looked into that a little bit, and that did seem to be an array of elements, but that's only going by their cartoons, so to speak. They don't really, wasn't able to get a lot of information out of those guys about how they're built or how they actually work, but the document or the marketing documentation sort of suggests that it was a square array of maybe 100 by 100 nanowires. So that'll be interesting to see if the diamond technology is going to be used in the same way.
Yeah, and even in networking, communications, DCQNet in Washington, D.C., they say we will have a quantum internet, national quantum internet. And this is going to have an array of, computers and sensors and all that type of stuff. And Fermilab and Argonne and in Chicagoland, they actually communicated both quantum and classical information all at the same time. Now, anybody else we haven't heard from? I saw Ron, you came on. You can go ahead if you want.
Well, I'm just taking all this in. Very interesting discussion. As you know, I'm a business guy, and we're looking for promising ventures in quantum computing. So if there are any suggestions for people to talk to or areas having significant potential, that's what we're interested in.
Yeah, it's becoming more mainstream, Ron. So back when I started, and I don't know, Nardo, when exactly you got in heavily researching.
Yeah, I got into it about 3 years ago, Kevin. But I've always been, I'm a technical person. I've done a lot of AI work, 6 AI products in the medical space. And I bumped into it via the quantum machine learning aspect of it. And Ron, if if you're interested in the conversation, I could tell you what the near-term, mid-term, and long-term aspect of quantum technology is.
Okay, great.
Yeah, and Ron, I've had a speaker on twice. His name's Russ Fine, Corporate Fuel Advisors. Russ is both technical and very business oriented when it comes to quantum developments. He's another one. There's many people. Christopher Bishop, he's transitioned from 12-year career in IBM, and then now he's a moderator at, it's called Quantum Economic Development Consortium. So I would check Chris out. And the list goes on and on. It's not hard to find people that are knowledgeable in quantum. Back in August, when I started a provisional medical patent, and it took a month. In September, in October, we had our first quantum in the industry IPO. That was October 1st, IMQ for over $1 billion. Ever since then, there's Rigetti, they're all $1 billion plus, D-Wave. I think CoQuanta, I think that's the other one public. I don't think that's quite as high. Those other 3 were SPAC deals. I also did a quantum timeline, so it's over an hour. It's got 235 sources in it, and it'll really catch you up to date because not only can you see the text, but you can see the meaning of it. So anybody else we haven't heard from, and you can come on again, Mike, if you wish.
Yeah, I think, I've seen a lot of different subjects covered here. One of the things that, so I've been in this business, 44 years, and in the quantum for 9. And there is a high differentiation between simulation and quantum, and they are radically different. One is trying to solve a search combinatorial space, and the other is trying to resolve differential equations, basically. And people haven't quite caught on to the fact that you have to restructure your problem into a quantum state where you say, I want the lowest energy, because that's what quantum's doing all the time. Every time it folds a DNA, that's what's happening. And that's what quantum computers offer. And that's a big task to take the applications of brain science into understanding what is the algorithm I want to solve in order to accomplish AI. And they're currently doing that on the wrong machines. Not the wrong machines, but machines that are the best for right now. But in the future, quantum is going to do it differently, quite differently. It's not going to be linear algebra anymore. So just a point I like to make.
Thanks, Mike. I appreciate that. So when we use that word simulation, he's referring to quantum being run on a classical computer. I also use the word simulation as far as for brain organoids, is that we want to simulate that with a computer. So,
Oh,
like,
actually, no, I'm using it for like weather model simulations,
oh,
car crash
okay.
simulations, for all the other physical simulations that we're using every day, airplanes, solving the Bernoulli equations around aircraft. The problem is that there's a whole bunch of problems that are not solved with a polynomial in a polynomial time. They create a search space that is fundamentally to us humans infinite. And that's a whole different computational area of which I want to resolve a problem that looks infinite. And what I find personally interesting is that problem looks, if a squirrel runs across my living room right now, that's a problem that looks highly different from working on simulation of a weather model. And it's a huge computational problem. And the fact the brain does it is exciting, but we can't figure out how to get a computer to do it because we keep thinking processes. That's all.
Awesome. Yeah, so definitely Rigetti, they're working on, I think, weather and fusion, the weather kind of simulation. And anybody else we haven't heard from? So there's been a number. So IBM Cleveland Clinic, they have a 10-year partnership, including quantum technologies. We have Sandbox AQ and Mount Sinai Hospital. They have a cybersecurity and quantum data partnership. There's one other kind of like big one, but it started, Fermilab and let's see, Fermilab and NYU Langone. It's a hospital in New York. They have plans to partnership to incorporate quantum technologies into MRI. So there's a number of good kind of development, and it's good to see kind of the commitment on like the common names as well. So anybody else we haven't heard from? So Karma, and then Austin, you can hop back on, or Dave.
Oh, well, Kevin, thanks for the introduction. It's always wonderful to hear the different perspectives. You're always a subject matter expert when you show up, and I'm just thankful to listen and learn.
You want to give a little bit introduction, how you associate with quantum medical or medical?
Oh, sure. I'm a co-founder with Dr. Faisal Shah Khan of Dark Star Quantum Lab. We have an epidemiology lab that relates to pandemics right now, and scheduling as a simple way to resolve issues using well-accepted medical concepts and procedures.
Very cool. I mean, you could keep talking about that for sure.
I'll appreciate that. I'll hold off for now, really without Faisal here to talk about it, or one of the PhDs running the lab. I'm just not going to do it justice.
I also want to mention another quantum expert, Denise Ruffner. She's very public. She creates these things as far as, I got this image, and it basically showed me all of the quantum hardware, companies and then the number of quantum hardware technologies there are. So she creates very good kind of like concise stuff, shares it in different presentations. There's an Austin, Texas one too as well. Anything, John?
No, just lots of reading and just insight. Basically, that's the best you can do, unless you're going to design something. You get an idea of what they're trying to do, and can you get involved with the technology part, that basically where the manipulation is going on in the experimentation. But other than that, it's just you're running your own simulations. We don't think like the brain thinks. We think differently. We're totally separate from the way the brain thinks. So until we can think like the brain thinks, or to go into Mr. Spock mode, you're really going to have problems trying to analyze what we're looking at. We're objectively looking at how the brain functions.
Yeah. And I would say a big hurdle to jump is basically a lot of neuroscientists aren't too aware of quantum. But I'd say even since 2019, they have quantum supremacy, and then they call it quantum advantage, or, these types of things. And then we finally get a cloud service in December 2019. And I would say most in the science field, academia field aren't too aware of it. So I would say to anybody reaching out to those people, you really have to spell it out as far as like the key, and especially in sensing. And even in June 1st, Xanadu photonic computer, 36 microseconds instead of 9,000 years. It's not a practical quantum computer. It's a specific task, but it's still something. And if we're at 216 photonic qubits, then that's where we're at. But I think a lot of the maybe just not misinformation, but non-information, like people don't hear too much about it outside of their realms in science.
We seem to be in the circuit stage. This is kind of like the early 40s computers, right? The circuit, we build a circuit, and we have to build circuits upon circuits upon circuits upon. So we're building a neural net or similar, some kind of concept of neural net. The idea is once you can get that free flow, and I say, get that free flow, the neural nets combined together and interface and we have them talk, then you'll have ability to basically go within or without boundaries more as you expand out.
Yeah,
I couldn't agree with you more on that.
Actually, there's a
because-
lot of people who think we're in the vacuum tube stage.
Yes, right,
Quantum
exactly.
computing, quantum devices are in the vacuum tube
Right.
stage.
Just getting
Or
the gates
mechanical
moving
relays.
around. Yeah.
And I couldn't agree with you more. I mean, you wouldn't go to a weather modeler and start explaining how to design a microcircuit.
Right.
The guy's up there worrying about partial pressure and temperature and those sorts of things.
Cells
So
and
why
cells.
are we asking neuroscientists to dive down into understanding qubits?
Right.
That's absurd, frankly.
Yeah.
And quantum networking is definitely going to be something different than what we understand as classical networking right now.
also,
Yep.
Rob?
Well, and again, I'm going back to the presentation that was done at the Washington, D.C. group. The gentleman there was very knowledgeable, and he was talking about the China's ability to transmit entangled photons from space, a satellite in space, to ground stations. And what it comes down to is a whole bunch of the equipment's not involved with the communications. It's just involved with distributing entangled photons or entangled qubits, and the communication happens after that. So, and all when you see work on that, you see people talking about one single bit. And so, you know, to get a network to scale up, you're going to need to have protocols to handle more bits, more connections. Everything right now is a point-to-point connection, and that kind of goes back to the early days of networking, like in DARPA or UUNet, where everything was a point-to-point. In UUNet, it was telephone modems. Had to call, you had to know your route through the network before you sent the message, and that's kind of where they're at now.
That makes sense.
Yeah, so but I mean, it's all very promising. I think the thing with networking is it's going to be a huge boost in the you know, via the quantum key distribution protocols that people are making money off of right now. That's where I think that's where the quantum internet will that'll be its, you know, its maiden voyage as far as getting quantum key distribution wherever they need it to go, and not just 40 kilometers away, or you know, whatever the limit of a fiber cable is. But as for actually using quantum networks to communicate, you know, send video or whatever, I don't think it's going to be different. It's just going to be used for other things. So that's my feeling.
I like the point-to-point analogy, because if you look at, I don't even know if we're at that stage of ARPANET in 1969, because basically we just have Washington, D.C., Chicagoland, you know, University of Chicago, Fermilab, Argonne, and then British telecommunications. I think those are the big ones. But it is interesting that we have fiber optics now. So in theory, we probably don't have to build everything from scratch like we did to begin with. So that's a possible plus there. So did you have something, John? And then anybody else?
Yeah, I'll say one more thing. I talk too much, but one of the things, you started this all off, and we're pretty excited about the quantum sensors. And I agree. That is an exciting place for you to go to better understand what the heck's going on with the brain, and to lock yourself into a dependency on quantum computing, which has got little to do with quantum censoring. I think your advancements are really going to be pretty strong, getting smarter, understanding what's going on in the brain. Because I'm clueless, but I'm amazed by the brain. And all the things it does. And I think you guys admit you don't really understand how it works.
Yeah, I mean, with all these neuromorphic computing that was this past month, they could do the same tasks, or they can do processing and memory in the same place like our brain. We're taking a lot of the things we're learning about the brain, or have learned, and starting to apply it in the tech world. So who knows, there could be a hybrid neuromorphic chip with quantum technologies or quantum mechanics, these types of things. But I think you're going to see that a lot. And I guess for anybody, especially joining, the call to action would be to start meeting with the key people in medical. And basically, you can't rely on them, because you have to research theirs, find out what they have, find out, what's slow, what's not possible in computation, and then in sensing, relay all this recent information to them as far as better magnetic reduction in noise. When I first started this journey, even last year, I was like, can't you use quantum to reduce noise in anything? And now it's not only sound recordings, you could potentially do it in other things too. So they use this, if you see in that, I posted in the chat, it's a 4-letter acronym, it starts with Q. And basically, they're saying because of this is why they can do all these things, where they take like a really noisy clip, and then it's crystal clear. And again, how all these things hold up, time will tell. But typically, if you're in nature, it's a pretty good start. And then go ahead, Austin.
Oh, I was just going to say thank you for that introduction. This is definitely exciting to watch quantum, which is a young field, help out neuroscience, which is also a young field and still growing and learning. So it's going to be cool to watch and see how they both play off each other. And, as you further research into neuroscience, because it is that young field, I always like to tell the story of I took a neurobiology and learning class. And the first 6 chapters that we had to read through of the textbook were about all these great theories and ideas and studies that have been done. And then the next 6 chapters were all about how actually we don't really know that much, and there's still a lot to learn. And that one theory that we told you about, it was one study done actually, and we haven't been able to replicate it since. So there's still definitely a lot more to know, a lot more growth, and it's going to be very cool to see.
Yeah, very cool. I like the school analogy there. So any other last questions or comments?
I had a last thought about the diamond sensors. I'm wondering what it'll do to the research that's going on with the people that are building apparatus to read brain waves and direct equipment, like in the prosthetics business, where they're using brain waves to move limbs, artificial limbs and stuff like that. I'm wondering whether these diamond based quantum sensors will accelerate what's going on there.
Like I said before, the big one in magnetic is OPM, and they say it's a quantum sensor because it's taking the brain waves coming from the body, either magnetic from the heart and potentially brain, and then it twists the atoms that are suspended, these rubidium atoms. So as far as what's going on now, my guess is just like they take it the best of both worlds. Maybe there's something better with something's going on now, and then this thing develops over the course of at least 3 to 5 years, and then following approvals, all that kind of stuff. But yeah, I think for experimental purposes, rats' hearts, that kind of stuff is good. But there's also the other stuff with noise reduction too. So if you reduce noise in analytical chemistry instruments that are coming from, line voltage or, just from sample, that you don't want to look at and understand it better using quantum technologies to reduce that too, there's many aspects to go, but I think for the kind of the clear thing is basically if you have a certain magnetic wave and it has 10 times more signal or 10 less noise, then that kind of like raises your eyebrows, right? Like, and it's not a new thing. This is 2022, that was 2015. But yeah, I would say, Ron, as far as like, you're going to see all types of not only just the current technologies, but the emerging quantum sensors, computing, learning from each other, and then making awesome hybrids, some a little bit more quantum, some a little bit more classical.
It seems like there could be quite a few possibilities. So this is great.
Yeah, and again, I think that maybe the biggest hurdle is the existing science community that knows very little about quantum. So if you say, I just need this good quality data, tell me what's really slow on your end, and then we'll work from there. And once they see their competitor or colleague do it, then I think they'll be even more intrigued.
Kevin, I just want to follow up on your last statement. That's so true. I'm involved with a medical tricorder, Star Trek medical tricorder project at the University of Waterloo. It currently does not have quantum, although the couple who put it together met in quantum class at Waterloo. They're itching to bring quantum sensors into their project, thinking that they had to go through the Defense Department for that, who had some of the equipment they wanted. What I've offered and what I will put out to you good people is for those who are interested in participating in a project like that, if you have a component to add to it, please contact me, and I'd be very happy to put you in touch with this couple. This is meant to be a large-scale cooperative project, and the couple is very nice. In fact, the young lady, PhD, professor of mathematics at Waterloo, was trying to save her husband's life, the physicist, and invented some technology that may have to do with quantum mathematics. I think she did it, though, through just her skill, but they have a sense for where this has to go, and just wanted to share that. So thank you for mentioning that, Kevin.
Yeah, and we can't end before saying NIST. So NIST does quantum sensing. It's hard to see exactly where they're at. A previous speaker, Marlu Slot, was on, and she's in kind of quantum materials. But if you're going to mention quantum sensors, I think you have to mention NIST. And I think a lot of their maybe earlier work wound up in that quantum.gov, quantum sensors coming to fruition article. So all very interesting. Okay, any other last comments?
I just had a quick question.
Yeah, go ahead.
So I know that we're talking about a lot about non-invasive, which is perfect, right? That's the gold standard for any kind of intervention. But when I think non-invasive, at least when it comes to the brain, usually I think of drugs. And as we start to learn more about the brain and our sensors start to get more specific, has there been any work on trying to get past that pesky blood-brain barrier, that keeps a lot of the really good medication from reaching its target points, or maybe even using that to find those target points or better target points?
I haven't heard of anything. So yeah, it sounds like a molecular kind of thing, like solubility, like dissolves like, because there's certain things like ethanol that crosses and other things. Yeah, basically all of the therapeutic drugs have some aspect, I think, hydrophobicity that they don't want to cross, but they're therapeutic.
Yes, yeah.
That was the catch. I think there's like all the things that in theory will work won't cross. So I haven't heard any other developments unless anybody else has.
Yeah, well, I've heard, Kevin, there is a drug discovery quantum AI type company out there that basically they work with biotech firms, and what they do is they dwindle down, molecule candidates from millions down to those that can basically pass blood-brain barriers, right? So yeah, the company is called Polaris QB.
Yeah. So the
You
CEO,
probably know them.
yeah, the CEO has been on the discussion.
Yeah, so they've done a lot of work in looking at looking at the drug design, molecular candidates, and stuff like that. That includes the blood-brain barrier passing.
That's interesting. I didn't know that as far as the blood-brain. I didn't know exactly what they were working on. So the other companies, Met and AI, and then Janssen or Johnson & Johnson are doing kind of like peptide protein work, Austin. And then I haven't seen too much recently from Janssen. I know Met and AI, that's solely what they do. And then with a lot of these is they're limited to the hardware, to quantum annealing, to like flatten a 3D molecule into a 2D space. So like approximations, like, a lot of approximations.
So you say they're limited? I mean, that's basically the company I just came out of, quantum computing. We were doing 100,000 size qubos. So I don't know if they ever talked about
Was that, go ahead.
Yeah, I don't know if that's their limitation. I mean, that's basically the code I wrote, which was originally QBSolve, but became QCI QBSolve, which we accelerated about 500-fold, and we could do really big problems. So the biggest problem was finding the people who needed to solve that big problem.
Yeah, as far as that kind of stuff, you're hardware limited. Quantum annealing is relatively less or relatively higher in fidelity, but it only does optimization problems, so it's not like for everything. So it'll be interesting. Now, what comes to mind is like
It's an interesting thought, because basically all NP-complete problems can be converted to all other NP-complete problems. So, which is basically they solve a QUBO.
Yeah, and even D-Wave, they're going to be implementing gate-based superconducting qubits, which are the theoretically most powerful, into quantum annealing and a CPA.
Yeah, what's funny about that whole philosophy is all they're doing with gate-based models is being able to do QAOA in order to solve QUBOs, of which, of course, they have to do it 1,000 times longer. But I mean, be careful. Some people have some entrenched ideas about what quantum has to be, and they're thinking process technologies, and quantum isn't a process. It's basically a collapse to a solution out of the lowest energy, like every peptide does or every time your body solves a DNA problem. It's theoretically impossible, but the gate model is, I'm just not buying it.
Anybody else before we log off here? And then if not, this has been episode 46 with Organoids and quantum technologies. Appreciate it. I'll probably post something else. It's going to be something like this, like primary literature focused, a good article, and then we'll have a discussion about it next Thursday. Appreciate it. Have a good rest of your night and have a good rest of your week. Take care. Bye.
Thank you.
Thanks, Kevin.